All right, welcome everyone. Welcome to the next lesson of the School of Solana. This is lesson, I would say 4, I think. And in this lesson, we are going to talk about the Solana programming model part 2. In this lesson, you will learn how you can actually call another programs from your program. So you have the smart contract or the Solana program and you want to execute or perform cross program invocation to different Solana program or different smart contract on the Solana blockchain. So we will learn how to do this on the Solana in the Anchor, and you will also learn about the PDAs, what the PDA means, what it means that the address is program-derived address. And yeah, that's everything from the introduction. I hope that you are enjoying the School of Solana. I can see that we can see that the Discord is pretty active. That's really awesome. I hope that you will learn something new during the lesson. You can definitely expect the hands-on example at the end of the lesson. And also we will have a quick recap from the previous lesson, which was Solana programming model part 1. I think everything was set, so we can go directly to the lesson. Firstly, let's start with the program-derived address, or you may know it also as PDA. In order to understand the PDAs, let's just quickly recap the accounts. So on Solana, everything basically is an account, everything is stored in accounts. We were talking about the structure such as hash map, where you have key and value pair. In this case, you can think about it as a key is the address of the account and the value are basically the contents of the account. We were talking about lamports, data field, flag if the account is executable. For example, there was also the owner, program owner, and so on. So this is the basic idea on the Solana, that everything is an account and it is stored in the validator. So the validator can load the accounts and use them for the execution of the program. The second part was about the address. So the address of the account or of an account is 32 bytes long public key. This is important in order to understand the PDAs, because most of the time you may know public key as a term from the key pair. So if you have public key, you should have the corresponding private key. But in this case, program-derived addresses are basically also public keys, but they are intentionally derived in such a way that this public key does not have the corresponding private key. And you may be thinking about why it is important that it does not have the private key. Then it might be not secure, but you will actually see that it is secure and it is pretty often used on the Solana. So let's continue to the motivation. On the right hand side, you can see the source code. This is actually taken from the part 1 of the Solana programming model. So from the previous lesson, and more precisely from the hands-on example. I created the data account in the Solana program, or I specified that we would like to store some data in the data account, and on the test side, or let's call it on the off-chain side, what we had to do was on line 9, we had to create this variable called data account, which was actually key pair. So regular key pair where it has the corresponding private key, and from this private key, the public key is derived. Then later on, where we were constructing and sending the transaction, we had to specify that the data account public key is going to be actually from the variable data account, from the key pair, and we had to also sign the transaction on the line 18 with the data account private key. This required signature is actually required because with the signature we were telling the system program that yes, we approve the changes that are going to be made to this account. More precisely, yes, we would like to initialize the data field here with the specified length, assign it to the program that we created, and so on. The motivation here for the PDAs is that imagine you have on-chain game, and for every user that plays your game, you create some data account which contains, for example, its username, some of his stats, how many experience, for example, he has. And if you do it in this approach using the key pair, what you would need to do is that for each registered user in the game, you would need to store the key pair, so the public key and the private key, or for example only the public key, not also the private key. You would need to store these in order to remember all of the addresses of the data accounts for the users of your game. On the other hand, if you use PDAs, program-derived addresses, these have the address derived deterministically. That means in order to derive the PDA, you need to specify seeds, which are optional, they can be also empty. You need to specify seeds, program ID, and there is something called bump, which will bump the address from the curve. But the idea is that you do not need to store all of the public keys of all of the data accounts of all of the users, because the address is derived deterministically based on the seed. So let's say in this case, in this example, you can create the address such that the first seed is, for example, the user's wallet address, the user's wallet public key. And the second seed is some static string, for example, player stats or something like that. And there are dedicated functions for this, but if you use these two seeds in order to derive the PDA, it will, and also the program ID and the bump, which are the next additional parts of the derivation, but you will see this. Then the address or the derivation process will always provide you with the same resulting address or public key without the corresponding private key. So in order not to actually store all of the public keys for the data accounts, you can utilize this determinism in order to always be able to derive the address. And you will also see it is used in cross program invocations. So if the PDA account, I said the PDAs do not have their corresponding private keys, but they still can be used in order to sign the cross program invocations, not the transactions directly from the off-chain or from the tests, but you will see that you can use them during the cross program invocations. This is from the motivation part. Let's now continue about what are the differences between the key pair and the PDA. As you can see in the picture, let's consider the curve. It is basically the elliptic curve where all of the public addresses, or public keys, where all of the addresses land on. Private key is just some random scalar number that is used in order to create the point on the curve. So let's consider your regular Solana wallet where you hold the meme coins, where you hold the Solana. So this wallet address has its corresponding private key, and this private key is used to derive the public key, and the public key then, my mouse is white so I cannot show you, but hopefully you see it, then the public key lands on this curve. So you can see we have Alice's wallet, 15 sol, and it is this point on the curve. Then you have the Bob's wallet, 27 sol, and it is additional next point on the curve. You can have someone else's wallet, and it will be somewhere here, and here, and here, and so on. The idea is that, the cryptography here is that if you know the point, which you obviously know because the point is the public key or the address, if you know the point, it is hard to find out what is the scalar or what is the private key, but this is just the security, this is just the cryptography, it is not that important. What is important is that the regular key pair and its public key always lands on this curve. On the other hand, the program-derived address always intentionally is derived in such way that the address fall off the elliptic curve. That means it does not have the corresponding private key. This is just the cryptography behind it. As I said, does not have the corresponding private key. And what is the derivation process? So it is derived from seeds, program ID, and bump. You will see for the cross program invocation part that program ID is really important in order to be able to create the signatures during the cross program invocations. And also you will see why the bump is important. Yeah, and the seeds are optional, so the field seeds can be also empty. But let's talk about the example. So this is again the elliptic curve part, and again you can see here lands the Bob's wallet, here lands the Alice's wallet, and here lands our Solana program. Solana program has also its corresponding private key and public key, because it is stored in the account. You send a transaction when you deploy the program, so it has corresponding private key and public key. But if you would like to store data in some account that has its address as PDA, so program-derived address, you can see that the first part here, seed, which is this blue one, is the static string called global state. So that's the first and only seed used here. Then the second part is the program ID. So you take the program address, which is the program ID. That's the second part. Here is the function called find program address. This function actually finds the PDA, and you can see that the counter account has the program-derived address, so it lands somewhere away from the curve. So you can see here is the curve and the PDA account lands somewhere else. And within the account we have stored value 126. So again, the idea is that you take the seed, you take the program ID, then there comes the bump that will be used in order to add some addition to the seeds. And as a result, we have the address that is kicked from the elliptic curve. So that means it does not have the corresponding private key. So, and what is the importance of bump? So it is really simple. Sometimes, or let's show it on this example, sometimes it may happen that you take the seed or seeds, if there are more than one, and you take the program ID. You create the PDA from that, but the PDA will land on the curve. That would mean you, on the one hand side, you derive the address, it is PDA, but it landed on the curve. That means it has corresponding private key. So for that case, you use the bump, which is just the addition. It is simple 1-byte number from 0 to 255, and you use that as an addition to the seeds. So if the resulting address actually landed on the curve, then you use the bump as an additional seed and rederive the address second time. And you do this in a loop until you find the first address that is away from the curve. Really simple, just an addition to the seeds to find the address that is not on the curve. Why? Again, it is because everything on curve has its corresponding private key, and PDAs do not have corresponding private keys. So you want to create something that is away from the curve, so it does not have the private key. That's the basic idea. If you understand it until now, you just understand the PDAs basically. Okay, and you may ask, what is actually the process of creating the PDAs? So it firstly starts with the find program address. You have the optional seeds and you have the program ID, sorry. Then you have the bump, which starts from the 255, and you take this bump and call the second function create program address, which uses the optional seeds with the bump and also the program ID. This create program address actually uses the seeds, uses the program ID, and uses the bump, and create the address from these values. Here is the check if the address is valid PDA. That means if it lands on curve or not. If no, then yes, it is valid PDA, and we are basically done. If it is not valid PDA, then we go to this no branch, we decrease the bump by 1, so we go to the number 254, and we do it again. So this time we have the seeds are the same, the program ID is the same, but the bump is decreased by 1. And this is done in a loop, so that until we found the valid PDA, then we created the program-derived address from the seeds, the program ID, and the bump. You will see more in the hands-on example how it is utilized within the Anchor programs. So what are the key points you should take from this part? So the main idea is that the PDA is address derived deterministically using a combination of seeds, a bump, and a program ID. So again, if you create the regular key pair, this is just the random private key and its random corresponding public key. So in order to store data or to create data accounts and also to keep track on all of the data accounts used within your Solana program, you would also need to store all of the public keys of the data accounts if you use the regular key pair. If you do not use the regular key pair, but you rather use the PDA, you know what seeds were used in order to derive the PDA, so you can always derive the PDA again as the derivation process is deterministic because, as I said, you know the program ID, you know the bump, and you know the seeds that were used in order to derive the PDA. It is address that does not land on the elliptic curve, so using the bump you kick it off from the elliptic curve, and it does not have the corresponding private key. That's the next point. And what might be important for you to know also during writing the Solana programs and tests, if you derive the PDA, you only derive the address. That does not mean that the account or the underlying account is automatically created on chain. So if you again derive the address using the process described in the previous slide, you just derived address, you just find the address, but the underlying account in the database is not initialized, is not created, is not anything until you obviously create it or initialize it. Alright, and lastly, I have a few examples to the Solana playground here, so feel free and look in the Solana playground. You will see examples using the find program address, create program address. So yeah, you can play with it within the playground, but we will have also the Anchor hands-on example at the end of this lesson. That was all from the PDAs, and now I would like to move to the Cross Program Invocation. In order to talk about Cross Program Invocations, let's just quickly recap what are programs on Solana. So program on Solana is a piece of code that is deployed to and runs on node validator, for example. But we were discussing also RPC nodes, so you can simulate there. But yeah, it is included to the network, so the program is actually deployed to the validators, and when you send transaction to the network that you would like to invoke the desired program, then it is basically called on or executed on each of the validator. Programs are similar to the regular Rust binaries, so for example, you may know it from, or also from the C++, you have the main function, which is entry point to the program. And on Solana, you do not have main function, but it is called entry point. And every program on Solana is basically executed using this entry point, and then based on the inputs of entry point, you perform the desired logic. So there is the dispatch, and based on the data, you call the specific instruction or function which corresponds to instruction. Programs are stateless, so meaning you can store any data in them. So if you call the program, or if you execute the program once and the second time, there is no some behavior that would actually that the program stores data in it or in some storage of the program, but everything you would like to store between the program executions, you need to store it within the accounts, or more precisely data accounts. And then yeah, last but not least, we use accounts to store, as I said, data and also program's code. So you take the source code, you call, for example, anchor build or cargo build SBF. These two commands create the .so binary, and you deploy this to the Solana network. So this is from the recap, and now let's continue to the Cross Program Invocation. So, as the name suggests, it is invocation which is cross-program. So one program invokes the instructions of another program. Pretty self-explanatory. Let's consider the image, or the picture. You have on the left-hand side wallet address, wallet account, regular key pair, for example, we have the signs. So yeah, it is regular key pair, as once again it has the corresponding private key. So yeah, you take the wallet account, you sign transaction and sends the transaction to the network. This transaction contains one or more instructions, and what it actually does is it executes or it invokes program A on the validator. Based on the instruction, it calls the desired functionality in the program A. But what can be also done is that the logic specified in the program A actually calls another program B, and some of the instruction from the program B. So this is the basic idea. As you would send the transaction from the off-chain part to the network in order to invoke the program A, you can do something similar within the program A to invoke logic from program B. You may, for example, ask, what about the signer privileges? So, signer privileges from the initial transaction invoking A extend to the B. That means if you are signer during you signed the transaction, I mean this transaction here, you sign it with your private key, then this transaction is sent to the network and the instructions within actually invoke your program A, and then within your program A you invoke the program B. The signature that signed, or the private key that signed the transaction, the signature is actually extended to the program B. So if you check in the program B, if the user signed the transaction, then yes, this flag will be true. The program B can additionally further CPI or cross-program invocation, can create cross-program invocation to another programs up to maximum depth of 4. And this is important regarding the PDAs. The program can sign on behalf of the PDAs derived from its program ID. You will see this during the next slide, how it's actually done. First of all, we have invoke function. We have basically two functions used for calling the additional programs. So we have invoke and invoke signed. The first one, invoke, is used when making a CPI that does not require the PDA signers. Don't be confused, I said yes, that the PDAs do not have a private key, so why are we signing here? But you will see it is actually possible due to the one fact that also, yeah, PDAs can sign, but the cross-program invocations, not the transactions directly from the off-chain part. From the example here, you can see that the invoke function parameters are pretty simple, I would say. You just specify what instruction you would like to invoke from the desired program, and you specify the accounts on input. So, for example, you would like to read from some kind of account in the program B, then you need to include it in the account infos here. And once again, signers provided to the caller program automatically extend to the callee program. So if you check in the program A, if the user signed the transaction, this flag will be marked as true. And if you do the same in the program B, then again this will be marked as true. It might have some security considerations because signatures add some kind of privilege to do some operations, so you need to be aware of this. You need to be sure that if you sign any transaction, you are aware of that in the program that you are invoking. This program may also invoke some additional program which can again use these signatures in your advantage or maybe in your disadvantage. And then the second function, which is called invoke signed, used when making a CPI that requires PDA signers. The seeds used to derive the signer PDAs are passed into the invoke signed function as signer seeds. And this is really important because as I was talking about the PDAs, in the PDA you have the three parts, the optional, or for the derivation of PDA you have three parts, the optional, seeds, the bump, and the program ID. It is important that the program ID is here because when you call the invoke signed, the runtime automatically includes the currently invoking program ID to the signer seeds. That means in the signer seeds you include the seeds, you also include the bump, and the Solana runtime automatically includes the program ID of the program which is currently performing the invoke signed. That means this invoke signed to the instruction with the PDA can be called only by your program, because there is the included program ID which is automatically included by the runtime of the program that performs the invoke signed. This is actually security consideration. When the CPI is processed, the Solana runtime internally calls create program address using the signer seed specified and the program ID of the calling program. This is the important part of the calling program. So if your PDA is used from some seeds, derived from some seeds, then from the bump and the program ID, this is often or always this is program ID of your program. If the program ID stores, if the PDA corresponds to the account that stores data of your program, then this program ID is going to be program ID of your program. This means the security consideration is here that this invoke signed with the privileges of this PDA can be called only from your program, because there the program ID is automatically included by the runtime. On the other hand, if everything was the same but from the different program, then that would mean the program ID is different. So in the end, the seeds provided and the program ID, or seeds, bump, and the program ID provided in the invoke signed will result in different address. That means the address on input and this one will not match. So you do not have, or the second program does not have privileges to perform the invoke sign on behalf of the PDA. Hopefully this was understandable, but yeah, it might be. I will also show you the hands-on examples, so hopefully it will clarify it more. And yes, basically, if a valid PDA is found, so again, the runtime calls the create program address using the seeds, the bump, and the program ID. If the valid PDA is found, the address is added as a valid signer. So That means you can actually sign, I do not want to say transactions, but you can sign cross-program invocations on behalf of the program-derived address. So it is used really often on Solana. So for example, you have escrow program. That means, okay, I will give you a small example. Let's say you have Alice on one side, you have Bob on second side, and they want to transfer funds. So for example, Alice has Solana, Bob has USDC, and they want to transfer funds. They will use escrow program, which basically Alice sends assets to the escrow. Here are the assets locked, and then in order for Bob to claim the Solana from Alice, he needs to invoke some claim instruction of the escrow program, which will also transfer the USDC from his account to the Alice's account. This means the Bob cannot scam Alice, so the transfer is actually atomically performed. And the idea is that you need to store the assets in some kind of vault in the escrow program, and you can do this using the PDA. So instead of having some kind of private key, for example, that has authority of this vault, you can have PDA as authority of this vault. That means no one actually can transfer funds out from the vault, only your program, because your program would do cross-program invocation to the system program transfer function, or SPL transfer, because we are talking about the USDC, which is SPL token. And then, your program would do invoke sign, cross-program invocation to the system program to transfer Solana to the Bob. To transfer USDC, it would also do cross-program invocation to the token program. And this everything will be done behalf on the PDA's or the program-derived address, because the PDA is authority over the vault, and as the program ID is included in the automatically included by the runtime, that means only your program can transfer funds out, because every other program would result in different PDA, as the program ID would be different. The important word here is the determinism, so hopefully this was understandable. You can again go to the Solana playground and have a look at some examples here. And now I would like to continue to the hands-on example. All right. So let's now work on the hands-on example, where I will show you the usage of PDAs or program-derived addresses, and also cross-program invocation. So we are again back in the Docker image in the Visual Studio Code, and the first thing that I would like to do is to initialize new Anchor project. You can see that the workspace is empty. So let's initialize. Let me open this a bit more, and let's initialize new project. And I will call the project and the program, I will call it program A, as I would like to show you how to perform cross-program invocation between two different programs in the workspace, which is also possible using Anchor framework to create also multiple programs in the workspace. And I would like to also show you how to create cross-program invocation, for example, to the system program transfer instruction. But let's start with the initialization. So this will initialize the workspace. Okay, we just navigated to the correct folder. Let me just restart the analyzer. And the second thing that I would like to do is to initialize the second program. Let's call it program B. So anchor new program B. Hopefully it is readable. So let me increase the font firstly. So yeah, with the increased font, we initialize the program A, and now we are adding new program to the workspace, which is going to be called program B. So anchor new program B. Press enter. You can see it was much faster. So created new program. I can hide the terminal and let me open the workspace. First of all, if you navigate to the programs folder, you can see that we have two programs in here. First one is program A, the second one is program B. Firstly, I would like to start with the program B, and I have already prepared the example in my mind, so this is just for playing purposes, but I prepared the example such that we will use cross program invocation in the program A in order to call program B. So what I would like to, for example, show you is that let's add new account to the context called, for example, PDA, and we expect that it is going to be signer. Right? Like that. I would also like to update this message. So what we can do is we can specify greetings from program B. And let me add this character in front of the context so Rust Analyzer won't throw warnings. So yeah, once again, we just specified that we expect the signer on the inputs of this instruction. The account, we call it locally we call it PDA account, and we just specify that we expect it as signer, and we modify the message that is going to be printed into the Solana logs. Alright, and now let's continue with the program A. So the first thing that I would like to do here, let me just copy this message. And let me insert it here. Sorry. Like that, and program A. Alright, so the first thing that I would like to do here is that I would like to specify the accounts that we expect here. As I said, we are going to use PDA, so we are going to specify PDA in here. So info, and then in the context, we specify PDA account. And you may ask, what is the account type here? So obviously it won't be something like program. It cannot be also signer, because PDA accounts or program-derived addresses cannot sign transactions, as they do not have corresponding private key, but they can sign cross-program invocations, as you will see. So we just use regular account info. Is there account info somewhere? Account. Like this. This is just the common type that does not specify any checks or does not have any checks. That means if you specify, for example, signer instead of account info, that means Anchor will automatically check that the account, or the corresponding private key of this account actually signed the transaction. If the type is account like this with the specified type, then the Anchor checks that the owner is your program, data can be deserialized into the structure, and so on. So that's the PDA account. For the transfer, I would like to also include receiver, or call it, let's say, in this case, signer, like that. All right. And when you want to perform cross-program invocations in your program, then you need to also specify all required addresses of the programs. So as I said, I would like to show you how to create cross-program invocation, for example, to the system program. So we need to also include system program on the inputs. So we include system program. Then I would like to also show you how to create cross-program invocation to the program that is also defined within this workspace, aka program B. So we need to also include program B on the instruction inputs. Let's call it program B. And this is important part. Anchor is really great framework because it automatically defines a lot of important stuff for us, for example, also for cross-program invocations. So what we can do right now, in order to be able to specify the type in this program part, the type that we expect the program B, so the anchor then automatically can check that the expected address or the address entered here is the expected address of the program B. What we can do is that we can specify the dependency here. Like this. And then, in order to use the CPI functionality that Anchor automatically creates, we need to specify feature that will allow to use the CPI functionality. So features CPI. All right. This should be it. And right now, in order to tell Anchor that expect program B here, we need to specify use statement, but use program B program and this part. All right, this won't show us the definition, but if you expand the program B with the Anchor expand, you can see the definition here. So basically the definition just implements, I think the trait is called ID or program ID or something like that. And you can use this program B struct within this part. So we tell the Anchor that this account provided as at this position is going to be program. That's why we have account type of program. And more precisely, it is going to be program B, which we used from the locally implemented program B within the workspace. So this is the baseline for the accounts, but I would like to also specify that the PDA account is actually PDA because currently it is just the regular account info without any seats, without any additional checks. So account info is basically general account on the Solana, so there are no checks performed. You can enter basically whatever account you want within this field. So I would like to add additional constraint to tell anchor that expect, for example, this account to be mutable. Mutability is required because we are going to perform cross program invocation transfer from this account, as you will see later. So the account has to be mutable. And also I would like to specify seeds, as the name suggests, that this account is PDA account. So I would like to specify some seeds that the anchor expects that the address is derived from. So to do that, specify account, brackets, and let's start with the mutability. So we want to explicitly say that this account is expected as writable or mutable. So use mute constraint. Then, as I was talking about the seeds, let's specify what seeds we would like the PDA to be derived from. This step is pretty simple. So it is an array of seeds, and you need to specify the string as a byte. So let's say this first seed in the seeds array is going to be some static string. For example, let's define it as PDA, or let's use, for example, Eki. I would like to also include second seed. So for example, for you to understand it better, the second seed can be, for example, also pub key of some account in order to connect, for example, the signer to this PDA account. So what we can do is we can specify signer.pubkey, and if we hover over those seeds, you can see bump must be provided with seeds. This actually tells us that we need to specify it like this. And I have a mistake. Okay, it is not pub key but key. And something like S bytes. Is it already correct? Maybe as ref. All right, it is all right now. Okay, so back to the bump. This bump here actually tells anchor, or there are two options how to specify it. You can use something like this. So you tell anchor when you derive address for this account with these seeds, always use 5 as a bump. In some cases, the address will end on the curve. In some cases, it won't end on the curve. If it ends on the curve, it is not valid PDA because it has corresponding private key. If it lands somewhere else than on the curve, it is valid PDA. But what we would rather do is do not specify constant value like 5 here, but we would like to specify it in this manner. And this means we are telling anchor use canonical bump. Canonical bump is actually bump that starts from the 255 and the address is created in a loop, and it tries to find the first bump that actually kicks the address from the curve. So it uses 255. If the final address is not on the curve, then it found the valid address. If the final address is on curve, then it will decrease the bump to number 254 and so on until 0. What might be important also to mention here, as you could see in the lesson, program ID is also part of the seeds, and the idea is basically implemented here, but you cannot see it. But yeah, when the anchor derives the address for this account and checks that the address is as expected based on the entered seeds and bump, it will also automatically your program ID, so this one. All right, so you cannot see it, but it is here, it is there. And I would also like to include mutability here, and I will tell you why. We will perform transfer from the PDA account to the signer. And transfer actually updates contents of the account. You may remember it was, I think, in the previous week where we were talking about the accounts. An account has field, for example, LAN ports. And we want to, or we want to create cross program invocation to the system program transfer instruction. But yeah, the transfer instruction in the system program will update LAN ports in PDA account and also signer account. We will transfer from PDA to the signer account. So that means both of the accounts has to be mutable in order for system program to be able to update the contents. Okay, let's now move to the function body, or to the instruction body. All right, so first thing that I would like to do is create cross-program invocation to the system program. All right. So in order to do that, we can perform invoke signed. Why invoke signed? We need this PDA account sign this cross-program invocation because we need to authorize that yes, we would like to transfer LAN ports from the PDA account. You will see, I will also show you how it behaves with just invoke instruction. But firstly, let's start with the invoke signed. All right, what are the inputs? So first of all, we need to specify what instruction we would like to invoke. Then we need to specify account infos. So these are basically accounts on the instruction input. And then, as you could see in the lesson, we need to specify signer seeds. These are the seeds that the PDA is derived from. You should remember that the program ID is one of the seeds. That means if you specify the signer seeds here, then the runtime will automatically include the program ID from which the CPI is performed. That means this CPI with this particular PDA can be performed only from this particular program. So let's continue with the instruction. We would like to use system instruction. So system instruction, press enter. Rust Analyzer automatically included these parts here. So invoke signed and also system instruction. And we want to perform transfer. You can see this look pretty simple. You need to specify from which pub key or from which address you would like to transfer to which address and what is the amount of LAN ports that you would like to transfer. So let's transfer from the PDA. Let me first obtain the PDA address. Like that. And take it and insert it here. And it expects reference, so borrow. Then we would like to transfer to the signer specified on the line 36. So we can do basically the same with the signer. Like that. Signer address and also borrow. And for example, we would like to transfer one sol, which is 1 billion, or let's say 1 and 9 zeros. So 1 sol. Okay, so this is the instruction part. Then we would like to continue with the account infos. So here we need to specify basically vector of or array of all of the accounts that are going to be used within the instruction. That means we need to specify the sender, the receiver, and also the program that we are going to call. So the first one is the sender. Second one is the receiver. Important is the method to account info, as we need to convert the signer is of type signer. So we need to convert from this type to the account info. And I think I need to borrow here. All right. And yeah, I forget the system program, as we are going to invoke the system program instruction transfer, then also specify system program, which again is within the context. Account info. I do not like the formatting, so give me a second. Sorry. Like that. And last part are the signer seeds. The definition here is quite tricky, but if you understand it once, then you can reuse it every time. So what is the definition? It is reference array, and then reference array again, reference, and then byte, expected byte. And the contents here, I will write it and then I will comment it. Then we also expect the signer address here. And then also the bump. And the bump, we can obtain it also from the context. Like that. All right, I forget signer address, so we should be able to perform. This should be within, so I made a mistake and it should be here, I would say. And then signer. All right, and we have only warning here, so we need to return the result from the invoke sign. All right, this should be everything right now from this part. So the next thing that I would like to do in order to show you completely the PDAs, I would like to turn this resolution to the false. And then we can perform anchor build. In the meantime, let's navigate to the tests. And the first thing that I need to do is to create the signer key pair. So left free, key pair, and generate. All right, then I would like to continue with specification of the instructions. So we can specify accounts. What is this doing? Okay, it is almost complete. And all right, so we do not perform any cross-program invocation to the program B yet. However, we perform cross-program invocation to the system program. So yeah, and I wanted to check the accounts. So the first one is PDA account. So if we go back, it is still building. So let's give it a minute. Yeah, it is not recommended to use account info, as this is really unsafe, but for the example purpose it is enough. Why it is unsafe? As I said, the account info type does not perform any checks, so in general this is not recommended behavior. You should always specify accounts with at least some type, so for example signer, account, and so on. So what we should do here is that specify the check and some random stuff, a key. And that's only account info, and this account nope. So let's build it again. You can see it passed this time, and we can continue within the test. So as it suggests, the first thing is PDA account, and currently we need to derive in the test, or let's say in the off-chain, the PDA address. So how we can do it? Maybe just the reminder, as I said, if you derive the PDA, it does not mean the account is created. You just derive the address from the seeds, which is deterministic behavior. So if you specify the seeds again and again, the same seeds again and again, the address will be always the same. So let's derive the address. Find program address, and then we need to specify array of seeds. It can be done with the buffer from. Here we need to specify the string that is used as the first part, so a key. Then the second one is signer vodka and buffer. And last but not least, we need to specify the program ID. As I said already multiple times, the program ID is also part of the seeds, part of the derivation process, part of the inputs of the derivation process. So we also need to specify program ID. So we can reuse this constant program here. So program.program ID. And that should be it. Now, this function will create public key and number, and this number is actually bump. We do not need the bump currently, we just need the address. So let's take the PDA, or let's call it PDA address, and let's take it and use it here. Then, as I said, we have the signer. So like that. And all right, let's consider this won't be included yet, as we are not going to create CPI yet. So we can for now forget about this program, and we just need system program. So I need to rebuild. And now let's include the system program. For that, we can use web3 system program ID. All right, we are almost done here. The last thing that we need to specify are signers. So let's go back to the program. PDA cannot sign, as it does not have corresponding private key, sign transaction, but it can sign the cross program invocation as specified or showed here. And the signer is of type signer, which actually can sign the transaction as it is a regular key pair landing on the curve. So we need to specify that this account signs the transaction. That means just enter signer here, and we will obtain signature. I almost say that it is complete, but I forget to actually transfer or airdrop funds to the PDA. Why? Because we are going to perform cross-program invocation to the system program or system instruction transfer. We want to transfer from the PDA address or PDA account, sorry, into the signer account one Solana, one Sol. But as I said, if you just derive the PDA, that does not necessarily mean, or there can be some funds if someone, let's say, transferred previously LAN ports to this account, but we expect that there are no LAN ports yet. So what we need to do, we need to airdrop LAN ports to the PDA account. How we can do it? I showed you the airdrop in the previous lesson. Just let me copy this from my example that I have on the second screen. And this is basically airdrop instruction that I reuse. So airdrop on input, there is connection, address, and amount. By default, I use this huge amount, and then confirm transaction and request airdrop. I reuse this often, so let me call the airdrop in this part. So the first thing, as I said, connection. So we can obtain connection from program, provider, and connection. Then address and amount. Address is the PDA, and I made a mistake. It has to be here because we need to use the PDA address. And the amount of LAN ports that I want to airdrop. So in this case, let's consider something like 500 Sol, so 509 zeros. All right, that should be it. So yeah, once again, we derive the PDA, then we airdrop to the PDA address, and then we call the initialize instruction from our program A. Signers are correct, and we will we will print the transaction signature. Let me double check here, but this should be all right. A key, signer seeds, bump is also used. Sorry, signer seeds, signer address, bump is also used. Okay, let's clear this. And let's call anchor test. All right, transaction signature, that is nice. Let me open the second bash. And, cd program, then anchor, then Solana test validator. Validator Solana. Okay, dash. Okay, it is starting. Let me close this. Okay, it is started. So let's go to the Explorer, custom RPC, and let me insert transaction signature here. So the first thing that should immediately pop or bump to your eyes is the success. So the transaction actually passed successfully. And let me increase the text. So yeah, as I said previously already multiple times, you can see timestamp, finality, it is, or confirmation status, it is finalized. But what is more important is that, for example, this part here. You can see that the fee pair, this fee pair is automatically inserted by the anchor, so not that important for us. This account actually pays for transaction fees. What is important for us is this one. This account is actually the receiver of the one sol, so that means that's you can also see it here, signer, and the account was writable. And this is the PDA, the third account, which has its balance decreased, so from 500 to 499, and it was writable. Then we can see the instructions. So this is unknown instruction, as we do not have uploaded IDL. So that means basically we can see the third account, which was system program. These are the instruction input data, not that important. But what is important, inner instructions. And this actually defines the cross program invocations performed in our program. And you can see that we performed the system program transfer. You can see program, which was basically system program, from address, and then to address, which is the signer, from is the PDA, and transfer amount in sol. So that's why the one is here. And you can see it was successful. Greetings from program A, so that's what we entered in the message macro. What might be also important, if we open this account, you can see that this account is the signer account, which holds one sol. All right, let me go back. Let me stop the validator. And I was talking about the other option, which is invoke, not invoke signed. So let's do the same, but to show you the difference, let's call only the invoke. It will tell us that it is not imported, so let's import it. And let's forget about the signer seeds. Let's comment out this invoke signed, and invoke does not sign the cross-program invocation on behalf of the PDA, so we are not approving the transfer here. So let me see what will happen, or let us see. So once again, let's perform anchor test. Okay, we can see some error message here. Processing instruction 0 cross-program invocation with unauthorized signer or writable account. You can see, or I have a nice hack here. Let's go back to the tests. Let's create try catch block. Let's copy the contents in, and let's print the error message. Okay, it will show error in the second line. So, all right, I like this output more. What is important here is that we've got into the greetings from program A. So until now, everything was all right. Even until this line, and everything was all right. Even until this line, everything was all right, because you can see in the logs, okay, you cannot see that the system program was invoked because it would be printed in the logs after the invocation, but in this case, in this part, it was still all right. When the error actually occurred was within the system program, because we did not specify, we did not use the invoke signed, which would sign the cross-program invocation on the PDA, on the behalf of the PDA account. In this case, the invoke just takes signatures from the transaction and use the signatures or propagate the signatures into the invoke. But as I said, PDAs cannot sign the transactions because they do not have the corresponding private key. So that's why we received the signer's privilege escalated, because the transfer instruction within the system program actually expected that the PDA address sign the cross-program invocation, which is not ensured currently because we just perform invoke, not invoke sign. So hopefully this clarifies the differences. And now I would like to utilize also, so let me use it as it was. And now I would like to also show you how to perform the cross program invocation, for example, to the program B. So I would like to remove this invoke. And let me also remove these brackets. And let me also remove this part. So process of writing CPI to the system program might be not the clearest one. So Anchor has slightly different approach, and it defines some additional stuff. So the calling to this second program within the workspace is, I would say, more clear. So in order to call program B, let's create a new variable called CPI context, which is returned from CPI context. And now is the important part. I specified the signer here. So that means the account is expected to be signer. This is similar, or let's say this is the same as for the CPI to the system program transfer instruction. But this time we have two options. We can create new CPI context or new with signer. That new with signer is basically same as the invoke signed. So you can see we have the signer seeds argument here. So the first thing is that we need to specify the program. So let me specify the program. All right. The program is actually account info of the program that we would like to call. The account info similar to this part, which is here. So the first one is accounts.program.b, but again to account info. And then we need to specify accounts. And for that, and let me also make it more readable. So we need to do it like this. And here, once again, so program B, accounts, initialized, and it is structure. If you hover over this, it will tell you that you should fill the fields. And why is only the PDA account here? Because it expects only the PDA account here. So what we need to do now is to give me a second. It expects pub key, so it should be. Oh, sorry. It expects the account info. PDA account to account info. Yeah, basically because everything has to be account. All right. What is wrong here? I forgot a CPI here. So okay, it looks nice right now. And now we need to use this context to actually call the desired instruction from the program B. So to do that, program B, CPI, initialize, and CPI context. And once again, propagate error. So again, we used seeds to sign the cross-program invocation, but this time we were doing it slightly in a different way. We used the new with signer. That means we could use signer seeds in order to sign the cross-program invocation on behalf of the PDA account. And then the created context, we just reuse it in the CPI initialize function call. We have the program B here in the inputs, so let me double check everything. Greetings from program B, and then greetings from program A, so we can distinguish. This should be all right. First of all, let me build it. Maybe what you can notice is that these signer seeds here are basically the same one as here, because it is, from my point of view, it is quite self-explanatory, because we need to sign with the same seeds that derive the same PDA, because we use PDA account here, and we use the same PDA account also in the transfer instruction. Okay, this is already done. And the last thing that I need to do, I need to also include the tests within, the program within the test site. So first of all, let me clear the try catch part, and that should be all right. Let me uncomment this, and yeah, as we have this import for the program A, also include the same thing for program B. And I would like to also create the same thing here for program B and program A, like that. Program A, this is correct. You need to rename the stuff in the test. So in this case, the PDA is derived from the program A, program ID. Same goes here, and we are calling instruction of the program A. So again, specify program A here. And lastly, program B is program B dot program ID. All right, this should be it. So let me test it once again. Okay, we can see that the test passed successfully. So open this, let me copy the signature, navigate to the second bash, and start the validator once again. It is initializing, it is started, and let's use the signature. Once again, the result is successful. Basically, this is the same. You can see that here we have program. These outputs are the same, +1, -1 sol. You can see the instruction. This is again the same. You can see the transfer instruction. But what is different is that this part, right? As we do not have uploaded IDL, so the Explorer does not actually knows what was the instruction name, so that's why we have unknown instruction here. But this is the program ID. You can see if I copy this program ID, and if I go to the program B, the program ID is the same as this one specified here. Let me minimize this part and back to the Explorer. What might be interesting is this writable part, and that's why, or that's because the account is specified as writable in here. I mean this part. That means the mutability is propagated also to the CPI. And yeah, that's everything from this instruction part. But what I would like to also mention is that during the program instruction logs that are also included in the Explorer, you can see, if I increase it more, you can see greetings from program A, program invoked system program, the invocation was successful, program invoked unknown program, so the program B. You can see the instruction name that was invoked. You can see program greetings from program B, and you can see some additional stuff, for example, how many compute units were consumed. Again, program returned successfully, and again, how many compute units were consumed overall, not only within the cross-program invocation. All right, and one last thing that I would like to talk about. Let me again stop the validator and go back here. As I showed you how it would behave for the invoke and invoke sign, I would like to also show you the same behavior, but this time not using the new with signer. Let me comment this part, but let's use just new without the signer seeds. So if I open it, you can see that it expects only program account info and then the account specified here. We do basically the same, but we do not use new with signer, which allows us to specify the signer seeds for in order to sign the cross-program invocation for the PDA account or address, but we use just new without the signer seeds, so the PDA won't be marked as a signer. Let's test it once again. And you can see that greetings from program A, all right. Program, this only once is the address of system program. So the program was invoked, then it was the successful message was printed, so that means it was invoked successfully. But then we receive signer's privileges escalated because cross-program invocation with unauthorized signer. That's because we did not create CPI context with the signer seeds, which would mark the PDA as signer, but we use it without, so that means the PDA is not marked as a signer. Okay, this is everything that I wanted to mention within this hands-on example. Let me navigate back to the tests so you can see it once again in order if you want to copy it or use it in the playground or something like that. This is the airdrop that I use, and that's basically everything. So hopefully this clarifies the PDAs and cross-program invocations more. I can show you that don't forget to also within the program A include this part with also the feature specified in order to be able to do the same stuff as I was doing here. So don't forget to use this dependency here. And yeah, that was everything from my side. I hope you enjoyed the hands-on example, and let's go back to the slides. That was everything from this lesson. I hope that you enjoyed also the theoretical part, also the practical part, where I was showing the PDAs and cross-program invocations, basically in how to write them, how to use them. If you have anything that is not clear yet to you, just discuss in the classroom on the Discord. Maybe there are some peers that would like to clarify to you, or you can also ping us in the dev help channels. So yeah, that's everything from my side. I look forward to the next lessons, and enjoy the rest of your days, and bye guys.